An infinite long furnace of 0.5 meter into 0.4 meter cross section is shown in the figure below. Consider all the surfaces of furnace to be black. That means the emissivity of the furnace is 1. The top and bottom walls are maintained at a temperature T1 is equal to T3, which is equal to 927 degrees Celsius, while the side walls are at the temperature 527 degrees Celsius. The view factor F12 is 0.26. The net radiation heat loss or gain on side 1 is, and we are given the Stephen-Boltzmann constant, which is 5.67 into 10 to the power of minus 8 watt per meter square per Kelvin to the power of 4. We know that view factor of similar objects remain same, so view factor of 1, 2 will be equal to view factor of 1, 4. So let's write here F12 is equal to F14, which in the problem is given as 0.26. Also, from the summation law of view factor, we know that sum of all the view factors for an enclosure is 1. Okay, so that means the sum of this, this and this will be 1. F12 plus F14 plus F13 will be equal to 1. So from here we can calculate F13 is equal to 0.48. Now net radiation heat loss or gain on side 1, let's write Q1 net for this. This will be equal to Q12 plus Q14 plus Q13. Now we know that Q12 will be equal to Q14 because the opposite surfaces are at similar temperature and same view factor, right? Therefore we can write Q1 net will be equal to 2 times of Q12 plus Q13. Now the expression of heat radiation from surface 1, 2 can be written as 2 times of Stephen-Boltzmann constant multiplied by T1 to the power of 4 minus T2 to the power of 4, because it is going from surface 1 to 2, whole divided by 1 minus emissivity of side 1 or surface 1 divided by cross section area of surface 1 into the emissivity of surface 1 plus 1 by A1 F12 plus 1 minus emissivity of surface 2 divided by A2 epsilon 2, and Q13 we can write sigma into T1 to the power of 4 minus T3 to the power of 4 whole divided by 1 minus epsilon 1 by A1 epsilon 1 plus 1 by A1 F13 plus 1 minus epsilon 3 by A3 epsilon 3. Now in the problem it is given that T1 is equal to T3 because both the surfaces are maintained at same temperature, and that is equal to 927 degrees Celsius. Therefore this entire term will be equal to 0. So we can write the net radiation heat loss or heat gain will be equal to radiation through 2 times of radiation through surface 1, 2, and this will be equal to 2 times of sigma T1 to the power of 4 minus T2 to the power of 4 whole divided by 1 minus epsilon 1. Now also in the problem it is given all surfaces are black. Therefore epsilon will be equal to 1 for all surfaces. Therefore this term, the first term, the second term, first term and the third term will be equal to 0. So we have only the second term, and that we can write here. And this we can write here as A1 F12. Okay. So from here Q1 net will be equal to 2 times 5.67 into 10 to the power of minus 8 into T1 is 1200 to the power of 4 minus T2 is 800 to the power of 4 multiplied by A1. Now in the diagram we can see that A1 will be the area of the side 1. So A1 will be equal to 0.5 times the length of the furnace. Let's say that be L. So we can write here area A1 will be 0.5 times of L multiplied by F12, which is 0.26. In the problem it is already given. Therefore net radiation heat loss from side 1 per unit length will be equal to 24,530.68 watt per meter. Okay. Also, one thing to notice here is that T1 is greater than T2. So there will be a loss of 24,530.68 watt per meter of heat from side 1. Therefore, the net radiation heat loss on side 1 will be 24,530.68 watt per meter. For more information, you can refer to the NPTEL course, lecture number 20, view factor, and the consecutive lectures on conduction and radiation by Professor C. Balaji of the Department of Mechanical Engineering at IIT Madras.